All right, so now we have this optimization problem that we actually need to solve. So let's really try to figure out what happens when we solve this problem. So let me write it down. What happens when we solve this problem? All right. Now we have this Lagrangian form, right? And what we're doing is that we are trying to solve an unconstrained optimization problem because it's simply like minimize this or maximize this. We don't have like constraints. And so how do we do that? Well, one way is, and that's like the most common way of solving any convex optimization problem, is that I'm going to find the derivative and set it equal to 0. And I'm going to find the partial derivative with respect to the variables that I'm interested in, set them equal to 0, and then just like rearrange terms to get the final result. So for instance, what I'm going to do is delta L, so I'm finding the derivative with respect to the weights, and that is going to give me somewhat this kind of an equation, and then I'm going to set it to 0. So I'm like writing the entire process in a single line and not like using multiple lines. So this is what I'm going to get. N is from 1 up to big N, alpha n, yn, xn equals 0. So when I'm setting it, I already found the derivative, I set it equal to 0, and this implies that I'm going to get some w value, right? And so my w value is going to be the summation of n is from 1 up to n, alpha n, yn, xn. Similarly, I have another variable that I need to find the value of, and that's my b. So I'm finding the derivative of L with respect to b and setting it equal to 0. So this implies that I'm going to get some kind of an equation that looks like this, alpha n, yn. N is, of course, all the n's, and then I'm setting them equal to 0, which implies, of course, now this equation doesn't really have a b, but we still got something, and so we'll keep that and see why this is important, right? So eventually this means that this summation n is from 1 up to n, alpha n, yn equals 0. So these are the results that we get when we found the derivative of L with respect to the variables and then set them equal to 0. And so these are the variables of the variables at optimality. Now I can use these values and plug them back into L. And that is going to give me the final result. And that is going to give me the problem that I'm like really interested in. So when I plug back all these values into my L of alpha, remember the L equation? Let me quickly remind you. So here is my L equation, right? And so it becomes L of alpha because my W's and B's, I somehow derived some value for them. And so I'm going to substitute that here. So that like everything becomes like in terms of alpha. So I'm definitely skipping the algebra because what I've done here is that I've found like the W's here and something here. And essentially, I'm going to substitute the values of W in my original equation. So let me see what I get. So this is something that I'm going to get. And you can verify this. N equals M. And as like N and M are points, are like the same points, essentially in the same data set. So it's just like I have to represent two different points. So alpha N, alpha M, Yn, Ym, xn transpose xm plus summation alpha n. So again, like just substituting these values, that's all I'm doing in the W trans half. Essentially, this is like half W transpose W, like the value for the Lagrangian. And then the next half minus n is from 1 up to n, alpha n, Yn, xn transpose. And the same thing for the other point, which is like m equals 1 up to n, alpha m, ym, xm. All right. So if we are looking at like this term and this term, right, they are pretty much the same. Just like by rearranging a little bit, we're going to get the exact same thing. So what I'm trying to say is that my L of alpha is essentially going to be minus half of, because that's the only thing that's different, right? Half and then minus like this 1 here. So that's the minus half. And then n is from 1 up to n. M is from 1 up to n again, same point. Alpha n, alpha m, yn, ym, and then this product xn, xm, plus the alpha that was there. All right. So this is like a standard procedure in constrained, unconstrained optimization, and there's like no dependence of L on W and B. That's what we were trying to achieve. Now it depends on like just one variable, that's my alpha, right? And that's why we use stationarity conditions. Stationarity conditions are nothing but these, like when we find the derivative with respect to these different variables and set it equal to 0 so that we can like somehow simplify our problem and make it easier to solve. So that's exactly what we did. Now we of course have to continue maximizing L with respect to alpha such that, so like I have to maximize my L of alpha such that my constraint, which is like alpha, should be greater than or equal to 0, right? And we also have like this additional constraint that got added as a result of the stationarity conditions. Sorry. Let me see. I think we are running low on slides. So maybe I need to add a few here, and let me add them and then we can continue because I'm guessing we'll need more. So quickly do that. All right, so going back to this particular slide here. Yeah, this is what I was trying to show you, this one here. We also have this additional constraint. We cannot just like ignore this. So we have like this n is from 1 up to n, alpha and yn is also equal to 0, and my alpha is greater than 0, right? So what I'm writing here is to maximize this subject to alpha greater than 0, and this summation n is from 1 up to n, alpha n, yn is also, was it greater than 0? It's also equal to 0. So is equal to 0. All right. So now, can I do something about this optimization problem? Well, I'm saying maximize L of alpha, and I see that in my definition of alpha there is a negative sign. So one like common procedure is that you can take the negative of this L and just say I want to do a minimization of this, right? So I can just like say minimize this entire thing, right? So minimize this L of alpha subject to these constraints. And so this is my optimization. This is my final optimization problem, which is in the form of like alphas, right? And having said that, let's go back and check what our original dual was, right? So we had this dual problem, right? All right, so here it is, right? So this is my original dual problem where I was trying to minimize over alpha this entire thing, right? Over certain constraints, the constraints alpha and yn equals 0 and alpha and greater than equal to 0. Well, we using the Lagrangian definition and using the stationarity conditions, we achieve at we arrive at exactly the same thing. And let me also write it down. Alpha and yn equals 0, and this like L of alpha is going to be of course this entire thing, and alpha is greater than equal to 0. All right, so the min-max optimization of the Lagrangian is equivalent to solving the dual in our problem, right? So this is equivalent, I would say, to solving the dual in the original problem. And if we are able to solve the dual, of course, we would have solved the primal, right? Because there is this relationship that exists between both of them. So first of all, this here is the end of proof, I would say here, end proof for finding the equivalence of this Lagrangian with the original problem, right? And what we have achieved here is that like we can go ahead and solve the dual because it's equivalent to this and then it's equivalent to the primal, and then arrive at whatever results we want, right? So let's focus on like solving that, and let's see what exactly we get when we solve that, because that's exactly what we're doing here. Okay, so when I'm solving the dual, right, when I'm solving this optimization problem, right, I should get some optimal variable values. So basically, because I will be solving for alpha, so alpha star, let's say, is the optimal, right? And how does that help us? Because like dual is, of course, the like one way of representing this optimization problem in a certain different format. But eventually we need my hyperplane. So I need my weights, I need my optimal weights, and I need my optimal bias, right? So I need my hyperplane. So what I'll do is, because there is this relationship that we derived earlier, so once I have this alpha n star, let me call it alpha n star, Using that, I can create, like solve for my W's because I have this relationship between W's and alpha. So I'll say my optimal weights are going to be this alpha n star yn xn, because let me go back. This is what we found here, right? So these are the optimal weights. So of course, when I've solved that problem for my alpha, I can get the weights. I can extract the weights from there. And then similar to that, like we can find B. Of course, it's not as straightforward as we think, but not as difficult because we have the Kkt conditions. So let me maybe write it down on the side, right? So we have these Kkt conditions where we have alpha n 1 minus yn W transpose xn plus b equals 0, right? So we had this. So let's say there is this alpha n that is not equal to 0. So if alpha n is not equal to 0, then if it's not equal to 0, that means it is a support vector, right? And so let us call it alpha s. Let's denote s by like support vector. And that alpha s, because it's not equal to 0, is going to be greater than 0, right? And if that is the case, then I'll have this ys w transpose xs plus b equals 1, right? So just like rearranging a little bit, and then I can get this b, which is ys minus w star transpose xs. So you can like directly get this from this equation. Now, all right, so with all these equations, with all these equivalents that we have created, what exactly have we tried to like come up with? What exactly are we trying to do with all this math? Well, first of all, primal and dual equivalence has been established, right? And because we established the relationship between the variables as well, now we are free to focus on the dual to see how we can work, because eventually we have to go in that infinite dimensional space that we talked about without like computational issues. So now we are going to build that process and see how exactly that happens, right? All right, before we jump into that infinite dimensional space, let's go over this example that we have looked at last time and see if we get the exact same optimal hyperplane that we got earlier when we directly solved the primal. So let's look at that. All right, so maybe I can use another, and let me make that up, that toy data. If you remember, we had like somewhat something like this, right? And then there were 2 points, and these, if I remember correctly, were the support vectors, and there was like one from this side. And what we got, like the exact hyperplane here, was the equation of that one was x1 minus x2 minus 1 equals 0, right? So the weights and the bias is known here. And what else? Like there, of course, we had the input, which was 0, 0, right? Two-dimensional, 2, 2, 2, 0, 3, 0. All right, and then the target vector, which was minus for these 2 points, right? And plus for the other 2. Now, in addition to these two, we also have something that's known as XS. And XS is nothing but the signed data matrix. So it's basically like X times Y, right? So I'll have 0 and then minus 2, 2, 0, 3, 0. So this is like the signed matrix. All right. So now what we'll do here is that we have our original problem, right? But we know how to, like the optimal hyperplane problem is like solving that quadratic program, like basically getting the QPAC values and then putting them in my QP solver and then getting my eventual G of X, right? So we can do somewhat similar here in this problem as well, except that what we'll get here are like my alpha values. And then utilizing those alpha values, I can go ahead and compute my weights and my bias, right? So let's try doing that. But even before we do that, we'll have to like sort of get the equivalence of the standard QP or the quadratic program equivalence. So this is like I'm just like stating that here. This is what the quadratic program in general looks like. And so what we'll do is we'll just like get the QPAC from our problem. Okay, this is AU greater than equal to C. All right. So it turns out that in our problem, we need to get that term yn, ym, xn transpose xm, right? And because we had that here, let me show you, right? We have this like huge term, and like what exactly is that in our problem? Well, in our problem, if you look at any like n-mth term, I would call it like xs transpose, right? Let's say this is like the n-mth term. This is nothing but this like signed matrix that we have, like y1 x1 transpose, y2 x2 transpose, and so on, yn xn transpose, that multiplied with the row y1 x1 transpose, because remember we need that xn xm, and so that's what we're going to extract from this just by looking at this. So we have again yn xn, not transpose, right? So essentially getting the nth row here and the mth column here, right? Just like quickly giving you an overview, will be my yn xn transpose times ym xm, right? And this term, by just like rearranging things, like yn ym will come out and xn transpose xm will be called gm. Not called, but like let's denote it by gm. All right. And so basically what was like this and this was nothing but like the signed matrix, right? This was because like the signed is nothing but y1 x1 transpose, y2 x2 transpose, right? All right, so why were we so much interested in my gm here, right? And so because we are trying to find the equivalence of this gm with in my like whatever term is there in my quadratic program, right? So mapping basically to the standard form. So my g of m, which is my xs transpose, which we just saw, is sort of equivalent to my q in my quadratic program, because that's the matrix that we see in the standard form, right? And the second term will have this p, because we have the alpha term in the second part of the like our problem. And so the second term is going to be this alpha, and my p instead is going to become like -1 transpose, right? So I have qp. Now I have to get my a, and a comes from my constraints, right? And my constraints are my in the standard form, these are inequality constraints. And when we look at our problem, we have one equality constraint, and then we have one inequality constraint. So we can like put them together somehow, like we can figure out how to do that. For instance, if, and this is like side work, I would say, if my y transpose alpha is 0, that implies that my y transpose alpha can be greater than equal to 0, or my minus y transpose alpha can be greater than equal to 0, right? And when I'm saying my alpha is greater than equal to 0, this implies that my identity matrix multiplied by my alpha is greater than equal to 0. So this information here will give me my A, which is nothing but just like the coefficients of my alpha, which are like y transpose minus y transpose and I. This is going to be my A. And then what was the other term? So that's like C. And C we can just like tell by looking at my original problem is going to be this like vectors of zeros, right? So 0 to n. All right, so we have Q, we have P, we have A, and we have C. All right, so let's move on to the next slide. And so we got my Q, P, A, C. I'm going to put them in a QP solver, and what I'm going to get is my U star. That is those were the variables in my original quadratic program, which in my case are nothing but my alpha star. And this is an example that has been taken from the book, right? And so the book already solved this problem, and the QP solver gave these values for alpha that are like 1/2, 1/2, 1 and 0. Let me check the book. Yeah, it says 1 and 0. All right, so I have alpha stars, right? And what does that signify in my original picture where I was talking about the support vectors? Well, these are my alphas here, right? So these points are my alphas here. So essentially this alpha could be half, and this is going to be half. This here is 1, and this is of course 0 because it's not a support vector, right? So that's what this is signifying here. While now the question arises, I'm still not done because like this alpha is like the variable in my dual, and so I still need my W stars and my B star, right? So I need those. And how do I get them? Well, we have talked a lot about them. So all I'll do is just simply substitute the values in here. That is alpha n star yn xn, and that, and this is just like a little bit of algebra here, half minus 1 0 0 plus half plus 1, the other one is minus 1 2 2 plus 1 times plus 1 2 0, and if you just like rearrange things and just like solve for them, you'll get 1 and minus 1. Similar for that, we had this equation for B star. Again, I'm not like jumping into the algebra. This was the equation for B star. Let me quickly, yeah, this one here. So if we just like substitute the values in B star, of course, we're going to get something like this. 1 minus 1, 0, 0, and that is minus 1. All right. So what is this? How does it help us? Well, uh, and this equation was like shown already, right? So this is like ys minus w transpose xs. And now because like we have my w and my b, I have to get my g of x, which is like the sine of w transpose x plus b, which is x1 minus x2 minus 1. All right, so this is the exact hyperplane equation that we got when we solved the primal problem. As you can see, like this was already stated here, this was my g of x. And what we established using this example, and of course, like we did prove that earlier, but now with this example, we know that this is the, like a dual is analogous to the original primal, the original problem. And if we look at this entire process, and we're going to talk more about it, but this is like also the algorithm for solving like the optimal hyperplane problem in the dual version, right? So now the next step here after this example is that we need to understand why is this relevant when we talk of infinite dimensional space, because that's what we started this lecture off with, right? So what we're going to do is we are going to revisit what our classifiers were in both versions of the problem and see how we are like where exactly we are getting rid of like the dimensionality, and we'll see an algorithm as well in the next video. So I'm going to stop this one here and see you in the next video.